Thank you all for coming to the session, and thank you, Laurent, for putting together such a great session on inflation. This is joint paper with Brandon Mayer and Brian Prescott, both from Atlanta Fed. So hopefully you can see it clearly from behind. The one sitting there in the morning, I cannot see that clearly. Anyhow, we ask this kind of special questions about the influence of price index, like a CPI, on firms' business decisions. The blue line in January 2015, more than 50% of firms tell us that changes in CPI has no influence or very little influence on their business decisions. Okay, this percentage declined from 2015 to 2022. But even in the high inflation environment in May 2022, 1/3 of firms still think that aggregate inflation like CPI do not really matter for their business decisions. So aggregate inflation expectations over most time period do not really matter as far as impacting their business decisions. And we got a problem, right? Because if we were eliciting aggregate inflation expectation, see we get something, then we were monitoring something that really doesn't matter. So to me, that's a wrong question. So is there a measure of price growth that is both relevant to firms and also closely connected to the actual measured inflation rate? So the answer is yes. If we ask firms for their own unit cost that they are aware of and they care about, by simply aggregating that across firms, we will get a measure of a proxy for aggregate inflation that tracks inflation rate very well. So we all agree, price depends on cost. Question here, how do we ask firms about their nominal marginal cost? So as pointed out by Alan Blender, this turned out to be a tricky question. Why? Because the term marginal cost is not in the dictionary of most business people. At the formation survey in 2011, the Atlanta Fed engaged in many face-to-face interviews to try to better understand what's the meaning of marginal cost for the business decision makers. So the result of the interview turned out to ask them about their unit cost. Now, unit cost for firms is equivalent to what we economists would think about marginal cost. Okay, so that's the language firm the most widely used to identify the cost of producing the next unit and service. So unit cost here including both the unit labor cost and unit non-labor cost. So let me give you some background about our survey. This is an online survey of about 500 C-suite executives, including CEOs, CFOs, and business owners in the Fed 6th district. So the survey has been conducted continuously since October 2011. So we ask probability questions about firm unit cost questions a year ahead on a monthly basis. Also, we ask them 5-year, 10-year ahead, like each quarter. So here's a screenshot of their questionnaire. Business decision makers are going to assign probabilities to each of these 5 pre-specified beans. Okay. Of course, when you add up the probability, this should be equal to 100%. Now, let me spend a few minutes here try to convince you the quality of the survey. First of all, as our panel include the firms within the Fed 6th district, this raises a concern of being representative. So in terms of both firm size and industry composition, the BAE panel is broadly reflective of the US economy. And we maintain a relatively high response rate, about 40%, in comparison to typical response rate in the firm level surveys, about 20% internationally. As we track the same firms over time, another concern you might have is that, look, these firms might learn over time, or the so-called tenure effect. So we don't see. There's no significant tenure effect in terms of both forecast errors or forecast uncertainty. Okay, so we interpret this as evidence that a firm that really telling us what's happening to their unit cost. And the way we track the same firms over time will not bias their responses. So finally, if we plot them, using simple scatter plot, we see that firms' expectations are closely related to their outcomes. Okay, having established the qualitative theories, the next issue is how do we analyze the probability distributions? So literature has generally taken two approaches, non-parametric approach, by simply assuming that the probability is focused at the midpoint of each interval, or parametric approach by assuming a distribution unimodal, like normal distribution we have seen, or beta distribution. So it turns out both distributions work well if we look at expert density forecast from ECB SPF. As shown in a recent paper by Carla Bender, Tucker McRoy, and myself in a JMCB article. So some firms, however, give bimodal distributions. Okay, to accommodate this bimodality, we adopt the so-called bimodal asymmetric paranormal distribution as proposed in the recent statistical literature. So let me give you one example. Hopefully you can see it clearly. Yeah. Okay, so what you see at the bottom of the screen here is a histogram. A firm would assign probabilities to two beings, but these two beings are not adjacent to each other. Okay, so neither normal distribution on your left nor beta distribution model would give a good fit. But however, the chart on your right, this is the bimodal asymmetric paranormal distribution provides the best fit. This simple illustration is further supported by some summary statistics, excuse me, like a BAPN distribution will give us the lowest BSA, lowest mean square error, and also it passed some misspecification test. Okay, so I'm gonna tell you this distribution is really powerful in the sense that it can capture both bimodality and unimodality. It is key parameters that can show for that. Okay. Let's dig into some details about this bimodality. After all, we don't see many discussions in economics. So cases of bimodality vary by industry, with manufacturing sector give us most bimodality, followed by finance and insurance. So as expected, firms that have bimodal distributions are typically much more uncertain. I'm gonna tell you the first moment mean expectation is the same, right? Whether you're bimodal or not, but the uncertainty is quite different. So why? We follow up with roughly 10 interviews, helping firms tell us more about their expectations. The majority give us some notion of conditional outcomes, right? If X happened, then my cost will be really high, but if Y happened, my cost will be low. Okay, in the next like 10 minutes, less than 10 minutes I have, hopefully I will show you some slides facts we had. First, in aggregate, we see that firms' unit cost realizations over the last 12 months closely commute with US inflation statistics. So what's interesting here is unit costs differ very much across sectors. So we are eliciting information that captures firms' idiosyncratic viewpoints. So we are not getting the same component. So however, if you aggregate them up, okay, by simply aggregating firms' unit cost realizations according to the industry share of overall GDP, we get an aggregate measure that tracks US inflation very well. Okay, this is this is my favorite graph. Okay, second, once aggregated, firms' unit cost expectations move closely with professional forecasters. Okay, here we compare firms a year ahead unit cost expectations against SPF. The chart on the left is their inflation based on GDP deflator. Chart on the right is CPI inflation. So let's dig into some details about the pandemic period. At the beginning of pandemic, sure I can. Here, at the beginning of pandemic, so what do you see here? Firms' unit cost expectation drop a lot. Okay, so this is sharpest decline we have. Sharpest decline to its lowest level we have on record going back to 2011. And this match up with those professional forecasters. So both firms and professional forecasters are convinced that early on the pandemic, COVID was a negative for inflation, and they viewed COVID as a demand shock. the supply shock aspect didn't occur right away, and it took some time. But when everybody switched, as you can see here, that switch was almost instantaneous. So far, we have a look at the performance of unit cost expectation in sample. So this table reports the result from our sample forecasting experiment. So our target is a year is a CPI, core CPI, PCE, core PCE, or GDP deflator. So first row give us root mean square Fox error from our benchmark ARMR11 model. So those are the raw numbers in the top row. All other numbers in this table give us the ratio against the benchmark. So if you see a ratio less than 1, implies we get a better forecast against the benchmark. So when forecasting CPI and core CPI, as you see, is highlighted in red rectangle here. So firms in the BAE panel outperform household, and these differences are statistically significant according to Diebold-Marino test statistic. And the firm's performance is comparable to professional forecasters from Blue Chip or SPF. So we see a similar picture when we try to forecast GDP deflator inflation rate. Okay, so this is the first point I try to make here in this table. Now, second, we group the firms into different sectors, sector 1, 2, 3, 4, because whenever I give a presentation of this paper, people ask, hey, is there some sector tend to dominate? If we look at the manufacturing sector, is there enough to check overall inflation? So we did this exercise. We group firms into different sectors: construction, sector 1, manufacturing, and trade, finally the service. Turns out none of the sectors tend to dominate. So each firm in our panel gives the idiosyncratic expectations on their unit cost. Turns out you need the firms across all sectors in order to aggregate up into a meaningful proxy for aggregate inflation expectation. So finally, we ask for probability distributions. We can look at the second moment or even third moment. Okay, but here I want to show you the inflation uncertainty. So this scatter plot of the unit cost uncertainty ex ante on the horizontal axis against the ex post absolute value Fox errors. Okay, so what you see here, there is a positive relationship between the two, meaning that more uncertain firms will have a larger Fox errors. So firms know what they don't know. If we aggregate them up, we get this a year ahead inflation Fox uncertainty measure. So until the start of the pandemic, you see inflation uncertainty was declining. We see the same pattern across firms in our panel, blue line, and also the dotted line is we get this a year ahead inflation Fox uncertainty from household survey in New York Fed. But since the beginning of the pandemic, household inflation expectations increased sharply and the uncertainty blew out. Okay, so our interpretation is that households were responding to the very sharp grocery price increases at the beginning of the pandemic. So this made them very nervous about what's happening to the inflation. But on the other hand, the firms are pretty confident regarding the pandemic impact on their unit cost. Right. So this is some new graph I want to show you. We asked this set of special questions that we basically borrowed from the Census Bureau's Small Business Pulse Survey. So we started to ask this in March 2021. We asked 5 times. We extend the Census Bureau's questions by going beyond whether or not firms are experiencing those supply chain disruptions, right? We extended that questions to try to get something. Hey, what's the intensity of these disruptions on their supply chains or operating capacity? Okay, so here you can see we plot disruption index on the horizontal axis against their unit cost uncertainty or unit cost expectations. The chart on the left, you can see a very sharp relationship between unit cost expectation the year ahead and disruption, but not less so for the unit cost uncertainty, the chart on the right. Okay, so supply chain disruptions are directly pushing up firms 1 year ahead unit cost expectations. Okay, I'm almost there. So to summarize, in the early months of the pandemic, firms on net saw the shock largely as demand rather than supply shock, as the majority of firms cut wages, lower selling prices, and lower their year-ahead inflation expectations. Throughout the year 2021 and into early 2022, among widespread and threatening supply chain disruptions and labor constraints, and against this backdrop of stronger demand, firms worked to pass through much of this increased cost, raising selling prices and rise up their year-ahead inflation expectation sharply, currently to a series high. So over the last few months, from the long-run inflation expectations, what I didn't show you here, like 5-year, 10-year ahead, have risen sharply to the highest level we have seen in decades. Right? This may be worrisome. This is worrisome for the policymakers. In June 2022, the average probability from the sign to the highest bins, plus remaining unit cost growth will be 5% or higher, was 31%. Okay, so more than double its pre-pandemic average. So I will stop here. I show you this online conference we organized on inflation dynamics in a new year of energy price shocks. If you are interested, please send a paper to this email address here, and there will be a special issue for the energy economics. Thank you.
Simon, so you save about 2.5 minutes for questions. If any, I want one simple question. We have a binomial distribution, so the mean doesn't mean we need center.
Agree. Because it basically gives the scenario forecast, right? If this happens, this might mean this might actually. If another thing happens, right, that's different, mean it's completely different. Absolutely.
The distribution is taking care of that more.
Yeah.
What I'm saying is, we know that the distribution doesn't know mean.
Agree. So we haven't seen that discussion. I mean, at least in the US SPF or ECB SPF, we don't see bimodal distribution. Right.
Simon, maybe you can say a few words about it. Is it online? Is it online?
Oh, yeah, okay. Oh, sorry. Yes, this is an online conference. Given the high uncertainty about COVID in the field, this conference will be in China as expected. So some cities in China still are locked down, right? We don't want to take any risk to go there. So this is an online conference. Yeah, thanks. Yeah, so we still have time. I mean, they working hard during summer, and yeah. So if you have any questions, let me know.
Okay, thank you very much, Simon. So let's move on to the next speaker. I'm going to prepare. Philippe, if you want. We need to share your slides with the Zoom. So this is what is going to be in this. Where are your slides? Not, you know? Okay, I hope they'll share.
Questo la mia devo tenere non l'avevo già tenuto su di slide share.
Okay, I think it's okay.
No.
Do you want this one?
Why is it? I'm going to toss it.
This one. Disable the bar. So we are hybrid mode, so you see, hide the bar, hide names. No, I don't know how to do that. So
hide closing.
Disable, hide. So,
all right. Well, hello everybody. We're going to talk some more about inflation today. And this paper is about doing deep learning to model and also understand inflation. And I guess more generally, from an econometric or machine learning standpoint, the idea is to write kind of neural network architecture that can actually learn something meaningful about latent quantities that we might care about as economists. You know, let's say you're at the central bank and you need to model something, but that something might not be in your Excel file. And that's, you know, it's a theory quantity and you need to estimate it somehow. And this paper is really about doing that for the particular case of inflation, but it turns out you can do that for many things as well. Okay, so inflation is back, I guess, as you're fully aware. A key macro equation to think about it is the Phillips curve. A Phillips curve, you know, as you probably know, we have a forcing variable that describes economic slack, difference between demand and supply, and PCs, Phillips curves. We've been doing them since the 60s, and thing is, in 2021 and early 2022, when you look at Phillips curve, you know what they were basically telling you is that inflation would be transitory. It sort of said, you know, if you look at the pressures coming from unemployment or maybe even the output gap, you know, what this was saying is that inflation shouldn't, you know, be as high as it is right now. Turns out this didn't happen, right? So it gets you to think, well, maybe this forcing variable that we're putting in our Phillips curve, maybe it's terribly mismeasured and it's been misleading us ever since. So like I'm saying, the output gap or economic slack, which I call GT in the notation of this paper, is absolutely important. It's a potential summary statistic of the macroeconomy to forecast inflation in the middle run, at least. And also it's the part that monetary policy can do the most about. So obviously it'd be good if we can measure it perhaps in a more accurate way. So obviously many problems with the Phillips curve, a bit like I just said, the output gap is unobserved. So are inflation expectations. I mean, we can observe many forms of them, but the inflation expectations that are relevant to predict inflation itself, I mean, it's unclear what they might be. Traditional remedies in econometrics is to create reasonable proxies. You can use filtering approaches. You can use factor models. You can use, you know, there are many things you can do, but they come with a bunch of assumptions, typically on the time series processes themselves, and it's unclear whether these assumptions are desirable. And what we typically do when we do a Phillips curve, then you do this sort of filtering exercise, right? You have your output gap, and then you throw it in some second stage, maybe estimation. And what people have been finding mostly over the last 20 years is that the Phillips curve is practically dead. However, the experience of 2021 and 2022 seems to suggest otherwise. So some machine learning perspective on all that. Most of the traditional paradigm is really on supervised learning. We're taking some measure, unemployment perhaps, the GDP, and we're filtering it somehow. Obviously, there are fancier approach out there now, but if you go to a central bank, you go to the Department of Finance Canada, where yours truly used to work a long time ago, that's what we used to do. We take some series, we throw them in some backstreaking filter or whatever, and then we get something, and then maybe we'll put that in another regression. And what we find often that it might not work so well. Now you can do also a data-rich approach. You can take, you know, the whole FredMD data set and, you know, extract a factor. It's going to be correlated with real activity, but it's uncertain whether that factor that definitely can explain a bunch of real activity variables, it's unclear whether it's going to really explain inflation. And, you know, if you're familiar with things called autoencoders, it's sort of nonlinear factor models, you can do that. The same problem will remain. You know, it doesn't mean that this latent factor you just extracted is going to be relevant to predict inflation. So deep learning comes to the rescue here. What we're going to be doing, we're going to be developing a new architecture called Hemisphere Neural Network. I'm going to tell you in 1 or 2 slides what this is. And the peculiar structure of that network is going to be nice because it will allow you to interpret some of the cells in that network as latent economic states, namely inflation expectations and the output gap. So that's kind of useful. The benefits are numerous. Nonlinearities, we can deal with them. High dimensionality also, I mean, it's a deep neural net, and the kind of data we have in macro wouldn't really scare anybody doing deep learning on the real deep learning data sets. You can estimate the output gap and its time varying coefficient in one estimation. Computations are rather quick. The black box is no more, at least you can look at the components of what you just estimated, and you know, in part at least, and you get pretty decent forecasts, especially for last year. So that's kind of good. Okay, so where does this hemisphere neural network comes from? These are going to be the only equations for today, or maybe one of the few equations. And nevertheless, the first equation is you know, not New Keynesian Phillips curve, as you've probably seen before. And what I do in the second and third equation is just to cast this as a, and you know, as a forecasting problem. We're going to forecast next quarter inflation. So the first component here you get are expectations, which are loosely defined. It's just a component about expectations because it's unclear. Obviously here it's sort of saying, well, it's next period's inflation expectation, but obviously, as you well know, it's unclear what horizon should matter to predict inflation itself. So a latent component summarizing expectation with its time varying coefficient. Then you have the gap or economic slack with its time varying coefficient. And then you have a component for energy prices. That's the third one. And then you have idiosyncratic shocks, because when Russia invades a country, it creates shocks. So you need to account for that too. So anyway, essentially this is, you can see that as sort of a three-factor model. We have three contributions from three latent components. And the reason why I'm using this H notation here to describe these three components is because these are going to be the outputs of some cells in this peculiar neural network. So what does the neural network looks like? It looks like this. It's rather simple, you know, from a deep learning perspective. It's going to be a fully dense, fully connected thing. But we're going to be having hemispheres rather than having, you know, one complete connected net. We're going to group variables, and you're going to have one group is going to be the real activity stuff. You're going to have another group is going to be the inflation expectation stuff, and you're going to have another group is going to be commodity price related stuff. And the idea is that all of these things enter the network, and they're not, you know, they're all processed in their own hemispheres, but they don't interact until the very last layer. So this forces the network to create 3 time series. These H's are really time series you can have a look at. And then it combines them in the last layer, like the green bullet right there. And this last layer is what I call the neural Phillips curve. These restrictions here obviously are restrictions. So it's a restricted, fully connected net. And somehow you can test those restrictions by looking whether this thing forecasts better or worse than a fully connected net. Turns out actually works a bit better. So what this is saying is, obviously from these restrictions, you get some form of regularization, but also you get interpretation because you force a certain separation of the data. Obviously, when you compare that to a standard Phillips curve, although this might seem restrictive, in fact, it generalizes the typical linear Phillips curve that we've been doing. And just from having this little separation there, like I said, you get interpretability and you get inflation forecast, but you can actually say, okay, well, there's something coming from the output gap, there is something coming from expectations. So in fact, you know, I was doing 3 hemispheres on the previous slide. We're going to be having 4 because I'm going to split the expectation one in a long run component and a short run component. And in the application of this paper, we just use the obvious data set and do the obvious thing. So expectation as inflation expectation from surveys. And we have lags of the CPI itself and lags from disaggregated price indices that you have in the FRED database. And for the output gap, we have labor market variables, industrial production, stuff from national accounts. So I guess, you know, the obvious stuff you would put in these hemispheres. One thing the structure I just shown you doesn't do is to provide you with a coefficient, right? What is going to be giving you are contributions. So it's going to be the product of the time varying coefficient and the latent component itself. But, you know, as we've been mostly discussing in macro for the last 20 years, we like to look at the gap and its coefficient separately. So in the paper, we develop a new architecture that I call HNNF. We're going to be seeing it on the next slide. And the idea is to bring back a bit more restrictions. And those restrictions will help you having a coefficient and a gap. And that you can do again by restricting what enters each hemisphere in the network. And this again is going to be somehow, you know, emanating maybe what people have been doing with standard Phillips curve. We have a coefficient that's moving very slowly, and you have the gap that is a function of a bunch of things. So the architecture is going to look like this. That one was a bit harder to draw. So really what we're going to be adding as a last layer, rather than just adding stuff, we're going to have like a linear multiplicative thing. And each hemisphere is a component of the model. You have an hemisphere for a coefficient, and the hemisphere is a function of just time itself. So the coefficient will be moving slowly. And then you have another hemisphere is going to be a function of everything for inflation expectation, but time, right? And you get that also for the gap. And just by doing these restrictions there, which we again can test whether they're valid or not by looking at forecasting performance, now you can get a coefficient and compare it to standard methods, and you can get a gap, the way we call it the gap, or at least economics lag. So yeah, it's about that. And then we're going to quantify uncertainty doing this sort of out of bag block subsampling, because obviously we're in a time series environment. So it's about that. So how bad am I doing on time, Laura? Really? Well, that doesn't happen very often. Merci. Merci. Let's keep talking then. Okay, so these are MSCs compared to the AR benchmark. You have like MSCs that include 2020, you have MSCs that exclude 2020. And obviously in 2020, pretty much any Phillips curve went berserk because, it saw this huge demand shock and say, oh, this looks like 2008, but even worse. Obviously, this was a bit of a different situation. So if you exclude these observations, from your forecast evaluation, what you can see, the red bars in that plot is that the 2H&N do pretty well. And they do better than the DNN. So that's the unrestricted deep learning model. RF is a random forest, typically works well for inflation. And then you have a bunch of PCs, OLS Phillips curve with the gap from the CBO. You have one augmented with expectations. And then the CKP is a traditional Bayesian way of doing the Phillips curve, where the coefficient is estimated, the unemployment is detrended. CKP means Chan, Coop, and Potter. So it's a nice Bayesian approach. I'm going to be using that thing to make a lot of comparisons. As you can see, it's doing a bit better than the AR benchmark, but not so great. And then we're going to have a look at the forecast, and we're going to see something rather interesting. So forecast here, yellow is again CKP. Think about this traditional filtering approach. And then H&N and H&NF. So the red one is the unrestricted network. And then the H&NF is the one where we have a coefficient and the gap. And as you can see, especially this is 2021, the yellow line is always way under the realized value, which is the bold black line, right? And that's basically, if you ask, policymakers, and I was at the central banker conference, they were saying, well, in 2021, we're looking at the Phillips curve, and the Phillips curve was saying a bit like Paul Krugman, there will be no problem. Turns out there were problems. So now if you look at H&N and H&NF, obviously the blue line and the red line are a bit more, I guess they were a bit more stressed in early 2021. They're saying, well, it might go up, and in fact it did. So as you can see, those forecasts are a bit more on the target, especially for this crucial period. It could end there, if we were doing traditional deep learning, I say, well, these are the forecasts, these are the MSC. But the point here is that, in fact, you can learn something from all that, about economics. So the slide here that I decided to call surprise is about looking at the gap in 2021 and comparing it with standard methods. Now I understand that this is a bit smaller than I'd like it to be, but sharpen your eyes for just 1 minute and follow me. Well, okay. So as you probably see, the blue stuff here, I'll do that. I'll cheat a bit. You see the blue line there, okay? That's, the model, the blue stuff is the gap as estimated from the H&N, right? The red is what you get from the traditional unemployment filtering approach, and the green one is what you get from the CBO. And as you can tell, the green and the red one are rather pretty much alike. The blue one, so this is estimated in the supervised pattern from the deep learning model, seems to have a very different story to tell. So obviously it's definitely more violently open in the 70s, but also, as you can see, and this is out of sample, the dashed black line is the beginning of our out of sample, small. And as you can see, the green and the red one have been in the negative region for pretty much all of 2021. In fact, the last data point here is the first quarter of 2022. And as you can see, finally in 2022, the red line goes and meets the blue line. But for pretty much all of 2021, those models say if there are any pressure coming from the real economy and inflation in this model, it is downward. Now, the model, the deep learning model that can estimate economic slack from a bunch of data on non-parameter supervised fashion has a very different story to tell. It's basically saying for the beginning of 2021, you have very, very high pressures from the real side of the economy. Now, second thing that's interesting about that graph, this is the coefficient, right? We've been saying, well, a lot of the traditional methods of pulling out the fixed curve was dead. The red line is exactly telling you that, and nothing really surprising here. Now, the blue line is the estimate we get from the model. And as you can tell, well, it hasn't been dying so much. So in fact, it was pretty weak during the Great Moderation, but then came back in strength during the 2000s. So really seems here the Phillips curve might not be there to measure economic slack in a bit more proactive way, if I can say it like that. So that's kind of important because obviously if you have a model like that, it's basically saying, well, there's some pressures from the economy that's bad or mild, and in fact, it's bringing your inflation forecast down. So obviously that would be great. This does better. And funny enough, there are a couple of papers finding that now when we change the measure of economic slack. And that's also matched the record of 2021. So just to conclude, we can look what goes inside the gap, right? So we estimated that gap and it looks different. Now the question is, what does the network do, right? It's basically a nonlinear weird regression of its own. So we just do this variable importance exercise to get a sense of what kind of variables are important to characterize this gap. So the first variable you see at the top is the L-Planet index, so HWIX. So obviously it's a measure of vacancies. And funny enough, if you look at that measure of slack in 2021, it's indeed skyrocketing. So what the network did basically is realize that this is a better predictor of inflation than unemployment. So this is more like the demand side of the labor market rather than the supply side. And we really found that this actually helps in forecasting inflation. Now, the second one, AWH man. So this is the number of hours work in the manufacturing sector. And what's funny about that is that unemployment is a measure typically about the extensive margin, how many people work. But this thing here, hours, is a measure of how intensely people work. So the intensive margin. So it's interesting that the network, first of all, looks at the demand side more than the supply side, and then looks more at the intensive margin rather than the extensive margin. And then you have a bunch of other things. But the last thing I'd like you to notice about this plot is the notable absence of GDP and unemployment. You have some derivatives of unemployment in there, kind of in the bottom, but most of all, GDP is not there. In fact, at some point, we even tried to filter GDP and filtered unemployment directly in the network, see what it would do with it. And it didn't seem to want to use it. So that's interesting. You can do these sort of things. You can do this also for inflation expectations. Now, the results are a bit less unorthodox, if I can call it like that. What you see, the first one, is the inflation expectation from the Michigan survey. So this sort of says, well, the current practice of using these expectations, a linear regression seems legit, if I can say like that. And then the second one are the lags of the CPI, which also says, well, maybe that's legitimate to use these things to model expectations somehow. And then you have a bunch of other things. So the SPI comes in third. So yeah, I think that's about it. Obviously, it's like a 50-page paper that talks about methodology and all that, but this is like the 15-something minutes summary. And I'll just conclude by showing you two vignettes that might be of interest. Using this methodology, you can also add a volatility hemisphere. Sometimes it's nice to do density forecasts. In fact, it's more than nice, it's often quite necessary. And funny enough, this kind of methodology, you can add a new hemisphere, change your loss function, and suddenly you can have an inflation model that does exactly what I just shown. It'll also have a volatility hemisphere going on. And as we can see from the volatility hemisphere, when the network failed pretty badly in early 2020, well, it actually knew it would fail because the bands just exploded. So it's kind of reassuring that when it fails, it might fail. And last vignette is that you can add pretty much any relevant component. We do two different exercises in the paper, but obviously, if you do something else than modeling the US, you might want to take account the fact that you have a small open economy, like in Quebec, where I'm from. So you might want to add an international component to your model. So, but the problem is, what do you put as an international component? You do a, you know, a composite of GDP. So nicely enough, you can just throw a bunch of GDP data in one hemisphere, and you can ask the network to actually create a summary statistic of the world economy, you know, economic pressure coming on your economy, domestic economy. And we did that for the US. And as you can tell, the international component doesn't have much action. And we can tell that the real activity and expectation that haven't been changed so much by this addition. But obviously for other countries, it might make a huge difference. So it's just, you know, to give you an idea of what you can do with this sort of things. There are other examples in the paper, but really the idea is, you know, maybe the parting words for this is that economic slag that is relevant for inflation might not be captured adequately by the usual suspects. And you can maybe use a deep neural network to actually find what matters. And then the HNN estimated up to 2019 Q1, Q4 actually, it sees considerable inflationary pressure in 2021, and whereas unemployment and GDP in their traditional filtered fashion did not. And what's nice now, you have a couple of papers that kind of re-estimated the natural rate of unemployment, or they say, well, maybe we should look at alternative measure of slack. And suddenly they find that the Phillips curve might be a bit more alive than it was. But this was a model that sort of discovered it by itself on data before 2021. So it's kind of nice we can do that using machine learning method. And finally, more generally, this work shows that economists can use deep learning to construct economically interpretable forecasts, which can inform policy. So that sounds about useful. That's about it. Thank you.
Unfortunately, our time will be one mark or one question. Maybe yes, just one. Thanks. I was wondering, have you compared against just the vacancy as your measure of slack and how well it is?
Yeah, so in the paper at some point we look, you know, the robustness checks, and it's actually a very relevant question. But no, I mean, you really see that the network sort of does a nonlinear transformation of it. Unknown it is, but still, like we did a version, we looked at, you know, can you use that and do a linear transformation and put that in a linear model? I just don't put that in the network directly. It doesn't seem to work. So you really need, you can use vacancies, maybe some other things, but you need to nonlinearly transform them so it works. Thanks. Oh, we're doing like a one step ahead forecasting here. So we're creating a gap and forecasting the in the short run. Well, we're just, you know, running a regression. So here's a predictive regression. So kind of pulls all the ranges. Anything else?
Okay.
Oh, okay.
Yeah. So let's move on. Okay. Thanks a lot, Philippe. So the last barrier between you and the lunch. So we have 15 minutes to conclude this session. So I'm going to talk about commodity prices and commodity jump risk. And again, we are in an inflation session. So we are going to see how we can use this measure to, in a sense, forecast inflation. So it's a joint work with two Greek colleagues, Katerina Karadimitropoulou and Thanos Triantafilou. So let me give you a bit of background, if I can move forward, and I cannot move forward. Yes, I can. Okay. So this is really an empirical work. So it's part of a research program that we have on uncertainty and the role of uncertainty on economic activities that is funded by the French National Research Agency. In the previous work, we used to work on uncertainty among commodities. Okay. And we show that, in fact, a commodity, a common commodity uncertainty shock is more or less like a demand shock, that is, there's a negative impact on growth and a negative impact on inflation. So this is one of the first results that we have, except for some prices, okay, energy prices. So here we continue this line of research by focusing on the possible usefulness of agricultural
commodity price volatility on inflation. Okay, and let me highlight that this is a very, very preliminary paper, and I expect a lot from this presentation. It's going to be the first presentation, and I apologize for the very low result that we have, but you will see that some of them are quite interesting. First of all, let me go back a few seconds on inflation, and we always see this graph on Twitter, on real social networks, etc. So saying that this is a ECB forecast and the inflation that we have in the euro area. So before the let's say the COVID crisis. So we know that in fact forecasts were much higher than we had. We had low inflation for a while. So I would just want to say that if you look at forecasts from central bank, you should keep in mind that forecasters have in mind inflation target. Okay, so we have inflation target. So we cannot go as far from the target. Otherwise, it means that the target is not a good target. So it has another issue. Okay, so people, when they comment this kind of forecast, they should keep in mind that there is a target forecast, inflation forecasts have in mind in central banks. So this is why we have this kind of price. Not that surprising. And today we are in the opposite direction. So it means that this is a forecast that the FOMC did in December 2021, and you see that forecast for inflation at that time, that is well before 2 months before the war in Ukraine. You see that the forecast was about the median was 2.5, something like that. Okay, so just before the war in Ukraine. So in fact, there is a sequence of shock affecting prices in a very strong way, making that it is very difficult now to predict inflation. So remember, the Queen asked, why did you, when economists were not able to forecast the global financial crisis? So we can have the same question here. Why are you able to forecast this rising inflation? Okay, so we have a bunch of factors. So we saw that the Phillips curve is at the core of the tool that people have in mind when they try to forecast inflation. So we have also commodity prices. We have also now an international view that is a complexity of bottlenecks in global value chains that are also playing on strongly on inflation today. Okay, so here I'm going to focus on commodity prices, okay, and see how we can get from this specific tool. So more specifically, we are working in this paper with agricultural commodity future. Okay, so we're going to take 6 agricultural commodity future at a high frequency, on a high frequency basis, and we are going to compute a jump tail risk measure. I'm going to show you what I mean by this jump tail risk measure. We are estimating a common a dynamic factor model to extract the common component among the 6 commodity future price volatilities, in a sense. And then we are using this C-jump factor into standard models to check if, in fact, this common jump risk, as we call it, can be useful. Okay. So main takeaway. So for the moment, I think, or I hope, maybe you can say the opposite, that we are maybe one of the first paper trying to focus on this topic, on the common jump risk component among agricultural future prices, which shows that it impact negatively inflation for US and for G7 countries too. We are going to show that, in fact, this measure also helps to improve the forecasting accuracy in comparison with the standard Phillips curve. And we also assessing the evolution over time. Okay, we know that, in fact, things are not linear, and that you can have a kind of evolution over time, especially when we think about commodity prices. It seems that, in fact, starting from 2004, something like that, we have a strong increase in the commonality among commodity prices, making that they are getting more and more important on market and also on the macroeconomy, for the macroeconomic activity. Okay. So what is this measure? In fact, we are looking at high frequency data. Okay, we are looking at 5 minutes data. Maybe the first paper for me using this kind of data. Apparently 5 minutes is something that appears to be decent for financial econometrician. We have 6 agricultural commodity future prices at the corn, soybean, wheat, coffee, lean hogs, and sugar. So the limitation, we have only the 6 variables, and the limitation to agricultural is due to the fact that data are quite costly. Okay, so we bought this database and we are planning to buy another database to look at energy futures to check if we can say something. Okay, so what we do, we compute a realized variance based on this high frequency data by summing the log, the square log return over a given month. So we have this realized volatility for each month. Okay, we start in 87 and we stop in 2019 due to data availability, in fact. So what is this GEMP component? So again, if we look at the financial econometrics literature, it turns out that there is a way to decompose realized volatility between something that is razor smooth, which is called a continuous component, and jumps, okay, around this razor smooth component. So we look at the B-power variation proposed by Barnhof-Nielsen and Shepard, which is in fact this equation 2, which is supposed to be something razor smooth. And what we call jump is simply the difference between the realized volatility that we have, okay, equation 3, and this razor smooth component. Okay, this is the jump component for each of the 6 agricultural futures. So what do we do in the second step? We take the common movement, okay, because we can have various things. So our idea, and in the previous work, that what we are doing is to say, okay, if we are extracting something that is common to the commodity, various commodity prices, in fact, maybe we can get something more related to macroeconomic activity. Otherwise, if you keep at the idiosyncratic level, maybe you have some shocks that are reflecting more supply thing than demand. So we try to focus on this, okay, and with the hope that it could be more strongly related to inflation impact. Okay, so we have a very basic dynamic factor model. Okay, very standard that we estimate. So this is F here. So we have the 6 jump component here, and this common factor is going to be our common commodity jump. Okay, so estimation is done in standard way. This is what we have. Okay, this is the shape of this common jump factor for agricultural commodities. Okay, starting in 87 and ending in 2019. And what we are doing now is to use this guy here and try to see how it relates to inflation and what can be done, in fact. So, in fact, if you want, we can have a kind of horse race models based on this factor, this tool here, this index, and see what can be said, okay? So the research question is the following: is this common jump factor useful to anticipate inflation? So for the moment, honestly, we have quite standard models. So in the previous session, James presented some nice quantile regression. This is obviously something that we can do. For the moment, let's think about very linear model for various horizon, 1, 3, 6, and 12 months. 12 months correspond to inflation, okay? What we have in mind, the annual growth of CPI, okay? So this is the equation. Standard OLS with Near West, and we consider A-line and core for US and G7. Okay. So what do we have? In fact, I'm going to show you some tables, but we tend to have a positive significant result. Okay, this is for the when we put simply, this is for headline inflation, so something more volatile than the core inflation. For headline, we have something. We have a signal, a significant signal, even when we're controlling for dynamics, short-term dynamics. Okay, this is what we have here. We have that this factor seems to be significant to a high with a higher probability. For cores are more or less the same, except the fact that it seems that the series is much more persistent. So you see in this column here, we have autoaggressive component that is super persistent. So it makes sense because core is more persistent. So the autoaggressive parts is more as a stronger variance in the explanation. So in any case, we see here that our factor is significant with a negative sign, meaning when you have an increase in the jump, it has a negative effect on inflation. Okay. So we do this for also for a line, and we take as a benchmark a Phillips curve. So it's not a fancy Phillips curve as presented by Philippe just before. This is simply we had an unemployment rate, if you want. Okay, so we can do something more elegant for sure. But what we have in that case is that it seems that our factor is taking part of the variance of the unemployment. Okay, this is for the headline, and for the core, this is true too. That is, if you estimate simply, I would say a Phillips curve for the core inflation, it seems that coefficient is significant, meaning that in our case, we get that unemployment is still playing a role. Okay, but once we integrate, this is a second table here. Once we integrate our factor, we see that the Phillips curve is no more present. That is, it seems that the factor is capturing part of the variance that is explained by the unemployment rates in some sense. Okay, so this is what we have for core inflation. So it is why I think it's worth to disentangle between headline inflation on one side and core inflation on the other side. Okay, so if we try to have a broader approach, as if to have a extended Phillips curve, if I can say that, especially we extend by looking at prices. You say, okay, why looking at volatility? Maybe prices are important, agricultural, energy prices, and metals, okay, plus exchange rates. So what do we get? So the first column is for H equal 1, and the last for H equal 12 months. Maybe let's focus on the last one. It seems that for the last one, so we have the exchange rate that is playing a role. It seems that the term spread is also playing a role. Maybe it's through the Phillips curve in a sense, we don't know. But what is interesting for us is that our index is significant, okay, is largely significant for all horizon, okay. So this is something that is quite encouraging at this stage, that is even with a linear model, very basic, it seems that we can provide something in the explanation of the inflation through this commodity jump factor, okay. Same thing for core, except that for core, what is interesting for core, if you look at the last column, we have inflation for sure there, past inflation, because we have much more persistence. And also we have, so our factor is significant. And interestingly, we have the metal prices here that are significant. And we know that, in fact, sometimes we take metals prices as a proxy for global prices. Okay, metal is supposed to be a proxy for global demand, in a sense. So we have this relation for core inflation, which is not visible for headline inflation, but it seems to make sense, at least for what we have. Same result for G7. Okay, I'm going to skip this, but we have this result for G7. So the second part is a more recursive analysis. So let's say if we want to assess the evolution over time of the drivers of inflation and maybe try to forecast too. So what we do a kind, for the moment, a recursive window analysis. So we start in 1982 and we increase one by one. Okay. The next step will be to do a rolling analysis to skip the first data to see what we get. So we do that recursive analysis, and also we did the dynamic model averaging approach à la Coupe and Kouroubilis to see how the factors are evolving over time, to see what we can get. So let me first focus on the recursive analysis. So this is evolution of our factor. So we can see that there is a clear downward trend, meaning that starting from 2000, we start to have a significant, or even before, a significant impact. If we look at the 12 months horizon, we have something significant starting from 1997. Okay, so during the global recession, it seemed that we go back to zero slightly, but then we continue. So we have an evolution over time. So over time, we have an increase in the impact of this factor on inflation. And this is true, in fact, for all the models that we have. Okay, so which is something quite reassuring for us. Okay, so we have this kind of graph, meaning that the importance of this factor seems to increase over time. So we can discuss why. Okay, it can be due to the financialization of the commodity market. It can be due to many different stuff. Okay. Let's have a look at forecasting now. Okay, for the moment, we just have a root mean square error. So we do that each time we have new data, we forecast for 1, 2, 1, 3, 6, 12 months. When we summarize everything, so this is for US headline inflation at the top and for US core at the bottom. So in bold, we have the best results. So we don't have for the moment the test, but let's think about just the best model in this respect. So the best model for, let's think about core, if you want. It seems to be quite difficult to outperform a Phillips curve, which is a bit not something that we could have expected, but for the core inflation, the Phillips curve seems to do maybe the best job. So best has to be quantified because we don't have the test for the moment here. Okay, but we will do it in the next version for sure. For L-line, it seems that it's a bit mixed, but in any case, when we use our jump factor with an autoregressive term, it seems to be not that bad. Okay. So now, if you think about G7, for G7, if you think about core, we have the fact that the Phillips curve augmented with our risk factor, the last column here, is providing the best result. Again, we don't have the test, so I'm not sure this is fully significant, honestly, just having a first view. But in any case, we have something that is seems to be interesting. And if we look at headline, in fact, for headline G7, we are able to a simple model, let's say with the common jump factor and an autoregressive term is doing well. Okay, is doing the, let's say, it's outperforming without any test. Okay, so please, I have this in mind. So what I want to say here is that it seems to be a clear, again, differentiation between headline on one side, which is super volatile and quite sensitive to this type of shock, and core, which seems to be much more persistent and less sensitive to this type of shock. With a Phillips curve, you can do something perhaps better with a simple Phillips curve, while for headline, we can add something. Last slide. So this is a dynamic model averaging at a Krupp and Koch-Obilis. This is something that we do for the US only. This is for headline in this case. So we look at the bunch of possible explanatory variable. And what is good with this approach is that we have over time the kind of probability of inclusion of each variable into the model. Okay. So we have all the variables here. So our jump factor is top right here. So for h equal 1, it's difficult to exhibit something clear. Okay, for very short horizon, we don't have any strong result. But when we increase the horizon, when we go to 3, 6, and 12, let me just focus on 12. We have something more interesting in the sense that we have a clear evolution over time of the probability of inclusion of our factor into the model. Okay, and this is true for 6 months too. Okay, so it means that maybe we so you see this is also for unemployment related to the Phillips curve, and some other variable here that is for energy prices, agricultural prices, not volatility, only pricing level. We don't have something very clear. But what is interesting for us is to see that we have a kind of evolution over time, and it seems that this factor is getting more and more important. Okay, so now perhaps the most interesting slide is what we have to do now. We have a huge to-do list to continue in this direction. And again, this is a very preliminary work, and I will be really super happy to have your view now or during the lunch. We want to, so we are a bit limited by the data because data are costly. Okay, so we want to extend the size, we want to extend the scope by looking at energy futures and maybe also metal futures that we know are quite related to the global economic activity. So this is something that we want to do when we will have the money. 1 and 2, 3 also maybe. If you think about Phillips curve, so as Philippe presented just before, so we can think about a more, let's say, tough model, that is by including expectations. For sure, we know that expectations are playing a role. Long-term expectations can be good, and possible non-linearities. Okay, so I'm not sure that we can do something with machine learning, but at least maybe adding some linearities by we have various models to do that. Even a simple tampering model can be super useful in this respect. And maybe also something that we have in mind is not only to look at G7 countries that are mostly net importing countries for commodities, but agricultural commodities, but also to look at exporting countries, like if you think about Brazil, for example, or big net exporting countries of agricultural commodities, to see what we get and how it impacts domestic inflation. And the list is huge. And if you have some other points, I will be happy to look at this. Okay. I'm stopping here. Thank you.